Hello everyone, my name is Mike and I have 10 techniques that I'm going to share with you for improving your group delay measurements on frequency converting devices that have an embedded local oscillator. And by that, I mean devices similar to this MyTech satellite block down converter, which is a device that takes a 20 gigahertz signal in on the back, uses an embedded local oscillator running at 18.75 gigahertz, and down converts the signal to about 1 gigahertz at the output. I want to measure group delay on a device like this, and this series of videos I'm going to show you 10 techniques to improve your results when you measure group delay. Now, of course, I'm going to use a Rohde & Schwarz ZNA vector network analyzer for these demonstrations. This instrument was introduced onto the market about 1 year ago, and it was designed specifically for this type of measurement on frequency converting devices. And the technique I'm going to use is called option K9. It's a two-tone technique for measuring group delay on devices with embedded local oscillators. And for more information on this technique, you can refer to the application note from Rohde & Schwarz. It's number 1EZ81, titled Group Delay Measurement on Frequency Converting Devices, and it goes into all the details behind the measurement, how the technique works, and how to optimize things. But we don't want to read the application note today. We want to cover it in videos, and that's what I'm going to cover in this series of 10 videos. So, for idea number 1 on my list of 10 ways to improve your measurements, we are going to talk about automating your measurement. Now, I have 3 reasons that I want to automate the measurement, and I want to take advantage of these 3 reasons throughout this series of 10 videos. Reason number 1, automating the measurement makes sure that I do not forget any settings. If I write a Skippy script file that tells me or tells the instrument how to set up the channel for the measurement, and I run that file each time I make a measurement, then I won't forget to make an important setting, such as, hey, let's change the resolution bandwidth filter to 1 kilohertz so we get a better signal to noise ratio. Or hey, let's make sure we remember to turn on the LO before I calibrate so that I get a good calibration. So I don't have to remember these things if I write a script file, and that's one reason I really like using a script file to duplicate measurement setups from time to time. A second reason that I like to use a script file is that it self-documents exactly what I did. If I automate the measurement with a script file and I come back to it 6 months later, I can look and see exactly what settings I used when I made the measurement, and I can duplicate the setup by just running the script file again. I don't have to take notes. I don't have to worry about forgetting to write something down. And my third reason for wanting to use script files for this type of testing is that it's very fast and very easy compared to setting things up by hand through the user interface of the instrument. So, of course, we need to know how to set things up by hand, and we're going to go through that. But once we've done it and we understand the settings, then it's very easy to put those settings into a script file so that we can take advantage of that going forward. Now, for this topic, I have 2 application cards that I want to share with you. The first one is using the GPIB Command Explorer tool on the ZNA. So this application card is just 2 pages. It goes through the basics of using the tool that is built into every Rohde & Schwarz network analyzer, which you can use to do this automated scripting. You don't need anything in addition to the network analyzer. Everything you need is built in to the analyzer the way it comes from Rohde & Schwarz. So no extra tools needed. You don't need to learn any programming languages, nothing like that. Everything we do is done in WordPad or Notepad on the network analyzer, and then it's just run through this tool to set things up. And I'm going to show you exactly how that works in this first video. The second thing I want to point out then is a second application card that I have on automated testing for group delay measurements. So this application card describes exactly how to set up the measurement of frequency converting group delay on the ZNA. So everything I'm going to show you in this video is already covered in the application card in case you want to skip ahead to that. But in the video, I'm going to show you how to do this step by step so that you can take advantage of the video or the application card. Okay, so let's get started. The first thing I want to show you then, of course, is how to set up the measurement by hand using the interface of the instrument to do everything we need to do. But as I said, I have 10 ideas, 10 techniques for improving the measurement, so I don't want to get ahead of ourselves. This first time that we set up the measurement, we are going to use all of the default settings available in the instrument. We're not going to change anything unless we absolutely must change it to make the measurement. That way, we can see what it looks like from the very beginning, and then we can progress through the 10 techniques I have for improving the measurement to see what each one does successively through the line. So let's start by just presetting the instrument and make this measurement changing the bare minimum number of things. So if I come to the instrument, first thing I always want to do before I start a measurement like this is to preset the instrument. Okay, that way we're starting from a known state. And just to be really sure in the future here, yep, there's nothing else running, just the VNA application. So from a preset state, I want to measure group delay on a frequency converting device. So the place that we want to go first is to the measure key. This is where we describe to the analyzer what it is we're trying to do. So the measure key is right here in the corner of the second display window. So we click on measure, and in this window we will see then two tabs for different measurements that are available. These really are just tabs. They show up as a radio selection, but here when I select S parameters, this just shows all of the S parameter measurements that are available to me, which are non-frequency converting type measurements. And when I select the mixer parameters, then this is the list of measurements that are available to me that involve frequency converting devices. So obviously in this case, I'm doing a frequency converting measurement, and the tab I want in this particular section is the two-tone group delay. This is the method we're going to focus on in this series of videos. So once I select two-tone group delay, I see that all the buttons are grayed out except the very top one, which is the setup frequency converting DUT button. So it's pretty clear that that's where I need to go first. So I click on this button and it opens up a dialog box. Now, maybe this looks a little overwhelming. Don't worry. We're going to change the bare minimum number of things. We're going to take the default settings in this dialog and use them for our first measurement. And then later we'll learn one at a time how to optimize each of the other settings that are available to us. Okay? So we're going to change the bare minimum. Now the first thing I want to do is look up here in the top box. This is how the network analyzer is expecting the device under test to be connected. It's going to create a two-tone signal using ports 1 and 3, and it's going to combine the signals with an external combiner. That's at least what it's expecting us to do by default. And so we are going to follow that. And here is a picture of how it's set up or hooked up on my network analyzer right now with this external combiner. So I'm just following their instructions. Port 2 of the network analyzer is going to measure the output of the device under test. Okay, we leave that alone as well. Now, the LO is embedded in the device under test. So typically, there will be no port driving an LO port on the device under test from the network analyzer. But we need to change this to be port 4 because there will be a calibration step. And during that calibration, I'm going to connect a characterized mixer, and that mixer needs an LO signal to come from somewhere. And we're going to get that LO signal from the ZNA. So I set that to port 4. That's the first change I've made so far. Nothing else has been changed. Now, working our way down the dialog, here is the sweep parameters, the area where we describe the sweep. Well, here I do need to make a change. This particular device that I want to measure is being swept from 19 gigahertz to 21 gigahertz, so I need to inform the analyzer of that. I'll keep the number of points and the power level. We'll keep those the same. The only other thing I need to change in here is the LO frequency that's used in the device under test and also during my calibration. I need an LO frequency of 18.75 gigahertz. So enter that value. And also I need 10 dBm of LO drive power from port 4 during the calibration step. So I'm going to enter that in this box as well. Okay, so I've made 4 changes. The sweep range and the LO frequency and power. This is all I've changed in the dialog box. Everything else we're going to leave the same. This is the bare minimum that I need to do to make this measurement. So far, pretty easy. That's what I would say. So let's say OK to close the dialog box. All right, now that we've set it up, all of these buttons are available to us. We have a setup channel where we can make measurements of any of these parameters. Now, what I want to measure is the two-tone or the group delay of the device under test. So that is the two-tone group delay button right here. By default, this trace is measuring S21. That is not what I want. That is a non-frequency converting S parameter. So since this trace is highlighted, if I click on this button, it will change this trace's measurement to be the mixer delay, the two-tone group delay measurement of the device that I'm looking for. Okay, so far so good. The next thing I need to do now is to calibrate this channel. Okay, so I'm going to connect a characterized mixer to the setup, and then we're going to press calibrate in order to calibrate the channel so that we take out the effects of all the cables that are interconnecting between the network analyzer and the device under test. So I've already set that up. It looks like this. Here's a picture, and this is all I need in order to do the calibration. Now the mixer that I'm going to use for calibration is a pre-characterized mixer. I measured it earlier, and I know its insertion delay, so I enter that value right here in this box. What is the delay of the mixer that I'm using for calibration? It's 190 picoseconds, so I can type that in like this, and now I know how long the characterized mixer is, and it can be used for calibration. So that's enough for us to already start the calibration. To do the calibration, we just press this button, mixer delay cal. At the end of that process, we then have a calibrated trace on the screen that is measuring the mixer, the group delay of the characterized mixer that's connected to the instrument. Now, is this an optimal setup? No, it's not. That's why I have 10 ways to improve the results. But this is a setup that does the bare minimum to measure group delay. Let's zoom in on the trace and see what it really looks like. So if I go to scale, I can auto scale the trace, and this takes me to a scale per division of about 500 picoseconds, or 1/2 of a nanosecond. And you can see on this scale, the trace is a bit noisy. If I was trying to measure a device that had 1 nanosecond of group delay, this trace would probably be too noisy to use. But on the other hand, if I was measuring a device that had 100 nanoseconds of group delay, then perhaps this noise would be tolerable for the measurement. In either case, we will see how to improve upon this as we go forward. All right, but for now, I just wanted to show you the bare minimum setup. Now, as I make improvements to the measurement, I need some metric to look at. So I want to add some trace statistics to this measurement, just as a metric that I will use consistently in the future videos, so we can see how we're doing as we make improvements. So to do that, I go to the trace config key. There's a trace statistics tab, and I'm going to turn on min-max peak to peak and the mean and standard deviation measurements, which popped up in a window down here. Okay, and I further want to constrain these measurements to be the central 40 megahertz of this sweep. The reason for that is that my channel is going to have a group delay response, and for comparison purposes, I want to really look at one narrow area of that group delay response where things are relatively flat. This way it'll be easier to see the improvements as we get them. So to do that, I select evaluation range. I pick a new range. I'm going to use range 1, and I enter what the range limits are. So as I said, the central 40 megahertz. So I will go from 19.8 gigahertz to 20.2 gigahertz. And just to make it clear what we're doing, I'm going to turn on these range limit lines. When I do that, then we see this is where we are making the measurement. This is where the statistics apply. Now, to make it a little easier to see, I'm just going to go to display, config, and make the font a little larger. Now, the metrics that I'm going to be looking at as we go through these videos are going to be the peak-to-peak variation within this 40 megahertz band, as well as the standard deviation. So standard deviation just tells me, well, they're both measures of how much my trace is fluctuating, and so they're both metrics I can use and both metrics I can watch as we make improvements to see the improvements. So what I want to note right now is that this peak-to-peak variation is very close to 1 nanosecond. So as I said, it's quite noisy, but it is the starting point for what we're doing. So what I've showed you so far now is the bare minimum that we have to do to set up this measurement by hand. Now, but the point of this first idea, this first technique I have for improving your group delay measurements is to automate the measurement. So I want to show you what that process looks like. All right. Now, I've already pre-written the script. It's a very short script. So what I suggest is we go to the desktop, open up the script in Notepad so you can see exactly what I did to create an automation script. And then we'll run that script to see that it duplicates what I've done here in terms of setting up the instrument. So let's go to the desktop and take a look. In the toolbar in the top, there's a Windows key. We can use that to get to the desktop. And in the desktop, then I have a script folder where I've stored different scripts. And of course, you're going to see more than 10 scripts because I'm going to go through a series of improvements. But for now, we're going to start with the script number 1, how to automate this two-tone group delay measurement. And I just want to open this up with Notepad. And let's make this full screen and take a look at how big this file is. So in fact, we see it takes up less than a page if I print it out. On the screen, it takes, just a bit more, but let's walk through the file and see what's all in there. Now, one thing that's in there is this add user query. This is a command that we can use in the script to pop up a dialog box to tell the user to either do something or to inform them what's going on. So I'm using a user query to just say, this is a file, this is number 1 on my list of top 10 things to do to improve your measurements, and I wrote this on the 22nd of April. So just a little note to me, hey, what file, what script am I running? Then I send a preset to the instrument, which you'll remember I did, as well as I set the start and stop frequencies. So very straightforward, just 2 Skippy commands for that. Then I set up the LO, just like I did in the dialog box. I use port 4 to supply the LO. I set the frequency to 18.75 gigahertz, and I set the LO power to 10 dBm. In this next one, I activate the mixer conversion mode for the channel. This is what made those grayed out buttons become active when I turn on a mixer conversion channel. Then I send out these commands. These were default settings in the dialog box, but I inform the instrument that my lower tone will be port 1, my upper tone will be port 3, and I'm going to receive the signal from the device under test on port 2. These next 3 are also things that are done automatically in the dialog box. I tell the instrument that I want to use the optimized mode for the second local oscillator, I want to use the coherent mode for the synthesizers, and I want to use the wideband path for the measurement. These are settings that are done automatically when you select frequency converting group delay in the user interface, but in the Skippy file, we have to explicitly pick what we want to do in these cases. All right, this next section here, these 4 commands, these are the 4 different ways we can create the two-tone signal. I have a whole video, we're going to go through those different techniques. In this video, we're just going to use the default setting, which is to use the external combiner, which you saw in that dialog box. All right, then I changed the trace from an S21 measurement to a mixer delay measurement. So you remember when I did that from the user interface. At this point now, I've set up the channel to do the measurement, just like I did by hand, a bare minimum number of settings. And so I pop up another dialog box that says, hey user, connect the characterized mixer because I want to calibrate this channel. So the user presses yes when they're done. We enter the known delay of the characterized mixer, 190 picoseconds, and we tell the instrument to take a sweep for calibration. When it's done calibrating, then I turn on a marker and those trace statistics that we talked about. I change the scale and zoom in on the trace a little bit, and that's the end of the file. I pop up one final dialog that says, hey, calibration is complete. You are ready to connect the device under test and make your measurement. So for me, this is a fairly straightforward and simple script file. And by using this file, it documents everything I'm doing. It makes the setup very easy, and I don't forget any settings, okay? We're gonna take this script file and we're gonna build upon it as we go through my 10 techniques for improving the measurement. But this is our baseline, and so I wanted to walk through it in detail in this very first video. But now, let's see what it looks like when we actually run the script, how that actually happens. Let's close this all out. So I'm back to my instrument, and let's go to a preset state so we're not kidding anyone. We know nothing's been done by hand. And now, how would I use this script file? How do I use this tool that I described that is built into every network analyzer from Rohde and Schwarz? First, you go to the application key, and then you launch the tool by using this GPIB Explorer button. Now, it'll pop up this little warning about a diagnostic command that was sent out. You can ignore that. It's not a problem. So I think we're going to hide that in the future, but for now, just ignore it. Now that the program is launched, I want to make it full screen over here in this little window, okay? And let's say update display as well. Go to local, bring back my Explorer. And the only thing we need to use in this tool is the ability to open the script file and run it. So that's all we're going to do. We don't need to worry about anything else. So I'm just going to go to File, Open Script File, and navigate to number 1, which was to set up this frequency converting measurement that we just looked at. So the first dialog box described the script file. The second dialog box says, hey, connect the characterized mixer for calibration. It's already connected, so I can say yes. And then the third dialog box says, hey, calibration's complete. We're good to go. So now if we look at this trace, we see the same thing we saw earlier. Okay, the scale is different. Before, when I did it by hand, I changed the scale to 0.5 nanosecond per division. So there, now it looks the same as what we saw when we did everything by hand, because I did the same thing as what we did by hand. So, and we see the peak-to-peak variation is on the order of 700, 800, and 900 picoseconds. So the same results as we had before. So this is what it looks like to make the measurement by hand and to duplicate that setup with the Skippy commands. So what I'm recommending as idea number 1 on my top 10 list of things you can do to improve your measurements is to start automating the measurements. You can do this very simple automation, and it gives you a way to document your results, to do the same thing every time, and also it's fast and easy. Okay, one last thing for this video before we wrap it up. So far, we did not connect to the device under test. As I said, we are going to measure something like this MyTech satellite block down converter. So far, we've set up the channel and we calibrated, but we haven't made any measurements. So let's do that. Now I have another box like that set up here. So I just need to connect the input and output cables to make the first measurement of this device under test. Now, I assure you, this is going to be a somewhat noisy result. We haven't optimized anything, but it's our starting point. It's what we're going to look at after we get through all 10 videos. We're going to do a comparison of where we started and where we end up. And so this is what we're going to have as the starting point. And I assure you, by video number 10, this trace is going to look super clean, super accurate. So don't worry about what you see right now. Instead, plan to go through the journey where we learn all the different things we can do to make this measurement even better than what you see. Okay, so let me get this torqued on. I want a good result, or at least as good as I can get with all these default settings. Now the trace is already off the screen, and that's because this device has some group delay, and we need to bring the trace back on the screen. So let's just drag it back down, and this device looks like this. Now, just as a reminder, I set up the trace statistics to be in the central 40 megahertz part of the band. Let's just re-enable those lines to remind us of that. Evaluation range, turn on those limits. So our measurements here are between these 2 points. And I also put a marker on the trace, and we're looking at a device that has about 7 nanoseconds of delay. Now, as I said, our trace variation is on the order of 1 nanosecond, so certainly too much in my mind for making a measurement of a device that has 7 nanoseconds of delay. So that's why we're going to go through the 10 ideas to improve this. We're going to make it much better. But this is our starting point. It's documented now. About 7 nanoseconds of delay. Peak-to-peak variation in the central 40 megahertz is on the order of more than 800 picoseconds, so getting close to 1 nanosecond. Standard deviation in this region is 180 picoseconds. So these are the numbers, these are our starting metrics, and we're going to work through 10 different ways to improve this. And at the very end, we will compare where we end up to this starting place. Okay? So for me, this is going to be an exciting journey. I love doing this kind of thing. For some of you, this might not be your cup of tea, so it might be a bit boring, but in that case, jump ahead. Just jump ahead and see the end game, okay? Because that's what will show you how capable this instrument is for making these types of measurements. For everyone else who wants the details, let's go through each of my 10 ideas one at a time and see how they work. I'm looking forward to it.